Welcome to the deep dive. You know, that bar of soap sitting by your sink. Today, we're going on a surprisingly fascinating journey into how it's actually made.
Yeah, it really is fascinating.
Our guide for this is the Handbook of Soap Manufacture by W.H. Simmons and H.A. Appleton.
A classic text.
We're thinking of this as a chapter-by-chapter exploration, really pulling out the interesting bits from this, deep well of knowledge.
That's the plan. This book, it really lays out the whole process. I mean, from the basic chemistry, how soap even works,
right,
all the way through the industrial methods, the different kinds of soaps we actually use every day.
So our goal today is to kind of unpack the key insights from each chapter, hopefully give you a new appreciation for this everyday guide.
Exactly, an everyday essential.
Okay, let's dive right in then. Chapter 1, Introduction. We all use soap, obviously, to get clean. But, fundamentally, what is it? What makes it work?
So, at its core, soap is basically a type of salt. It's formed from fatty acids, and the key thing is its detergent action.
Detergent action.
Okay.
Yeah.
Its ability to kind of bridge the gap between water and, oily dirt. Imagine a molecule, right? It has two different ends.
Okay.
One end loves water hydrophilic. The other end avoids water hydrophobic and prefers oils and fats.
So, magnets with different poles?
Sort of. So when you wash, the hydrophobic ends grab onto the grease, and the hydrophilic ends stick to the water.
Ah, I see.
And this kind of tug-of-war pulls the grease off so it can be washed away. The book also mentions hydrolysis, water playing a role in the action, too.
So these tiny little molecules are doing all the work. And the book mentions the history, too. Soap's been around forever, hasn't it?
Oh, absolutely. It's ancient. But understanding why it works, that's more recent, really the 19th century.
Okay.
Thanks to chemists like Chevreul and Berthelot. Their research was crucial for figuring out the chemistry of fats and oils and how they turn into soap.
Right, moving it from just craft to actual science.
And precisely. It paved the way for, making soap much more efficiently and consistently.
And the core reaction is called saponification. Sounds very scientific.
It does, but it's the heart of soap making. Basically, you take fats or glycerides, think glycerol molecules with fatty acid bits attached.
Okay.
And react them with an alkali, like sodium hydroxide, caustic soda.
Or potassium hydroxide.
Or potassium hydroxide, caustic potash. This reaction chops off those fatty acids from the glycerol.
Right.
The fatty acids then form salts with the alkali, and that's your soap. Glycerol is left over as a byproduct.
So fat plus alkali equals to soap. Soap plus glycerol, broadly speaking.
Broadly, yes. The book even gives the specific chemical equations for common fats like stearin, palmitin, and olein.
Okay. But I bet there are ways to speed that reaction up. The chapter mentions accelerating factors.
Yeah, you can definitely nudge it along. Heat is a big one. Like most reactions, more heat means faster results.
Standard chemistry.
Yep. Electricity was also looked into. And interestingly, biological catalysts, ferments, enzymes.
Enzymes, like in digestion.
Sort of, yeah. Things like castor seed ferment, steepsin, emulsin. They can speed up the breakdown.
Wow.
And then there are chemical reagents, strong acids like sulfuric, hydrochloric acid, something called Twitchell's reagent.
Twitchell's reagent?
Yeah, a specific catalyst, plus metal oxides like lime, magnesia, zinc oxide, and of course the alkalis themselves, soda and potash. Lots of ways to push the reaction.
Quite the toolkit. Okay, chapter 2 then. Constitution of oils and fats and their saponification. Sounds like the ingredients themselves are pretty complex.
Oh, they really are. That's a key point. Oils and fats are incredibly diverse. Plant sources, animal sources, their makeup varies a lot. Mixtures of organic, inorganic stuff sometimes.
And they melt differently.
Exactly. Different melting points. Some are solid like butter, others liquid like olive oil, even when cool. The book even calls them frozen oils.
Frozen oils. Interesting term. So not just one generic fat.
Not at all. And chapter 2 revisits some of the history here, too.
Right, the chemists who figured this stuff out.
Yes. We mentioned Scheele discovering glycerol back in 1779. But it was Chevreul, between about 1811 and 1823, who really dug into the details.
What detail?
The actual chemical structures, the fatty acids, the glycerol, how they fit together in fats and oils. His work was foundational. He basically mapped it all out.
And the main structure is triglycerides. Hear that term a lot.
Precisely. Mostly triglycerides. Remember the glycerol backbone?
Yeah.
A triglyceride is just glycerol with 3 fatty acid branches attached. The book shows the general formula.
Okay, 3 branches. But then it mentions mono and diglycerides.
Right, so you can have just one fatty acid branch that's a monoglyceride or 2 a diglyceride.
Ah, okay.
And even within those, The book points out there are different forms depending on where on the glycerol the fatty acids attach. So more complexity.
So if I take something like, say, olive oil, it's not just one thing, it's a mix.
Exactly right. Most natural oils and fats are cocktails of different triglycerides derived from different fatty acids.
So mixed triglycerides.
Yeah, the book calls them mixed glycerides. A single glycerol might have different types of fatty acids attached. The exact mix depends on the source, the plant or animal, and even temperature can play a role.
Okay, now the fatty acids themselves, saturated and unsaturated, those are the main types?
Those are the big categories, yes. Saturated fatty acids are in the stearic series: acetic, butyric from butter, palmitic, stearic, all single bonds between carbons.
Okay.
Then unsaturated, mainly the oleic series, they have at least one double bond between carbons. Oleic acid is super common. Also linoleic, linolenic, and ricinoleic acid.
Ricinoleic, that sounds specific.
It is mainly found in castor oil. Each series has its own general chemical formula.
And these different acids give the fat and then the soap different properties, like melting point.
Absolutely. The book lists examples: formulas, melting points, sources. Butyric acid gives butter its smell. Palmitic is big in palm oil. Oleic in olive oil. Ricinoleic in castor oil. It mentions other series too: linoleic, linolenic, ricinoleic, each behaving a bit differently chemically.
The book mentions a technical point about unsaturated acids reacting with bromine and iodine. Why does that matter for soap making?
Good question. That reaction with bromine or iodine happens because of the double bonds. It's the basis for tests, like the iodine value.
Iodine value.
Yeah, it measures how unsaturated a fat is, how many double bonds it has. This is important because unsaturation affects how the oil behaves during saponification and the final soap's properties like hardness or how easily it might go rancid.
Okay, that makes sense. So circling back to breaking down these fats saponification, Chapter 2 adds more detail to what Chapter I introduced.
It does. It reinforces the methods like heat and electricity, but goes deeper into enzymatic hydrolysis.
Using enzymes again.
Right. Lipases like that castor seed fermenter steeps in, they act like biological scissors, speeding up the breakdown into fatty acids and glycerol, often under milder conditions than, say, boiling with strong alkali. The book mentions researchers like Muntz, Lintner, Green who studied this.
Interesting. And the chemical methods, acids and alkalis.
It elaborates there too, using sulfuric acid, linking it to processes by Gay-Lussac and Twitchell, hydrochloric acid with Lukovich's method, and of course using alkalis like sodium hydroxide, NaOH. It shows the general equation for that hydrolysis, which is the direct path to making the soap salt itself.
Right. Okay, let's move to Chapter 3. Raw materials used in soap making. Feels like we're shifting from the pure chemistry to the pantry, so to speak.
Yeah, pretty much. This chapter lists all the different things that actually go into the soap kettle on an industrial scale. It starts with the main ingredients, fats and oils, which we now know are super varied.
But not just pristine fats?
No, it also mentions using recovered waste fats, plus some less common oils, oils with limited uses, even some newer fats they were exploring back then.
Waste fats. Sounds very practical, even for that time.
It was. Makes economic sense, right? Especially for cheaper soaps. The book mentions oils like Mora seed oil, Chinese vegetable tallow, showing the sheer range soap makers could use.
And then rosin. I know rosin from violins. What's it doing in soap?
Good point. Rosin, colophony, from pine trees. It's added to some soaps, according to the book, because it boosts lather.
More bubbles.
Exactly.
Yeah.
And apparently makes the soap a bit softer, too.
Okay. And then the crucial ingredient, alkali. Caustic soda versus caustic potash. What's the difference they make?
Huge difference. It really determines the type of soap. Caustic soda, sodium hydroxide, usually gives you hard bar soaps.
The kind we mostly think of.
Right. Caustic potassium hydroxide leads to softer, more liquidy soaps. Think liquid hand soap, shaving creams. The chapter also mentions carbonate versions, but the caustic ones are the main saponifiers.
And salt, just regular table salt.
Yep. Sodium chloride, it's used in a process called graining or salting out.
Graining.
After saponification, adding salt makes the soap less soluble in the leftover liquid, the lye. So the soap sort of clumps together and separates out. It's a refining step.
Clever. And lastly, soap stock. What's that?
Soap stock is a byproduct from refining crude vegetable oils. It contains some soap formed during that process, plus other stuff. The book says it can be used to make lower grade soaps, another way to use everything up. Resourceful.
Very. Okay, Chapter 4. Bleaching and treatment of raw materials. So some ingredients need cleaning up first.
That's right. Things like palm oil, cottonseed oil, animal fats like bone fat, even rosin. They often have colors or impurities you don't want in the final soap, especially if you want a nice white bar.
So bleaching is mostly about getting the color out.
Primarily, yes. Decolorization. Natural pigments can make the soap look, well, less appealing. Bleaching either removes them or chemically changes them so they're colorless.
The book mentions a specific one, the bichromate process for palm oil.
Yeah.
Sounds chemical.
It is. It used potassium bichromate and hydrochloric acid. The book even shows the chemical reaction, how it targets the color compounds in the palm oil.
Were there other methods for other oils?
Yeah, it mentions alternatives. Crude cottonseed oil might get treated with sulfuric acid or a mix of sulfuric and nitric acids. And a more general approach for various fats was using absorbent materials like fuller's earth or animal charcoal.
Like a filter.
Kind of, yeah.
Yeah.
They basically soak up the impurities, including the color.
Okay, chapter 5, soap making, the main event. It lists a whole load of different methods.
It really does. It's like a catalog of techniques. Direct combination of fatty acids and alkalis are the modern way. Then the traditional cold process, making soap under pressure, making soft soap with potash, marine soap for seawater.
Marine soap, wow.
Yeah. Hydrated soaps, smooth versus marbled soaps, different boiling techniques like pasting, greening out, boiling on strength, and that key one, fitting. It's a real historical snapshot.
Fitting keeps coming up with the boiling method. Why is it so important?
It's crucial in that traditional boiled process. You boil the fats with lye in stages, getting stronger. Fitting is the final adjustment phase. It's about carefully separating the pure soap, the neat soap, from the spent lye, and this darker, impure layer called nigra. Getting the fit right was key for quality.
And this boiling lets you make hard bars versus softer soaps.
Exactly. Like we said, soda lye gives you hard soaps through boiling. Potash lye gives you the softer, jelly-like soaps. Different alkali, different texture.
I was intrigued by transparent soaps. How did they make those clear?
Yeah, that's cool. Usually they dissolve finished soap in a solvent like alcohol or glycerin.
Oh, really?
Yeah, it makes a clear solution. Then the solvent evaporates, leaving the transparent soap behind. Clever trick.
And marbled soaps, those swirls, just adding color at the end.
Pretty much. Pigments are added while the soap is cooling, but still liquid. They don't mix in completely, so you get those veins and patterns. A bit of artistry involved.
Definitely. Okay, chapter 6. Treatment of settled soap. So the soap's made, but it's not finished yet.
Not quite. The settled soap from the kettle still needs more work to become the bar you buy. This chapter lists all the finishing steps.
Like cleansing? Is that getting rid of leftover lye?
Precisely. Washing out any residual alkali so the soap isn't harsh on the skin. Really important.
Then crutching. What on earth is that?
Huh. It's an industry term. It means stirring the hot, semi-liquid soap, originally done with big paddles called crutches.
Ah, hence the name.
Exactly. Later, mechanical mixers. Crutching is when you add all the extras. Builders like sodium carbonate or silicate to boost cleaning power, fillers like talc, and of course perfumes and colors.
And liquoring and filling.
Liquoring is adding a bit of water or weak lye to adjust the consistency, make it easier to handle. Filling is adding inert stuff again, maybe talc or starch, mainly to add bulk or change the texture, often in cheaper soaps.
Neutralizing, coloring, perfuming seems straightforward. Anything tricky there?
It's so straightforward. Neutralizing is just a final check for excess alkali. Coloring and perfuming are about appearance and scent. The chapter also mentions adding disinfectants at this stage for, well, disinfectant soaps.
And then the physical shaping. Framing, slabbing, stamping. Getting it into bars.
Correct, framing. Pour the liquid soap into big molds to set into blocks. Slabbing. Cut those blocks into slabs. Then there's piling them up to dry. Ring open and close piling is a specific way to stack for airflow.
Drying is important then.
Oh yeah. Reduces water, hardens the soap. Can be air dried on racks, maybe using warm air. Then stamping, pressing the brand name or design onto the bars. And finally, cooling before packaging.
A lot of steps. Chapter 7 covers toilet, textile, and miscellaneous soaps. So different soaps for different jobs.
Absolutely. This chapter shows how they tweak the basic process for specific uses. Toilet soaps, for instance, usually made from better quality fats, often super fatted.
Super fat.
Meaning a little extra fat or oil is left unreacted or added back in to make it milder, more moisturizing. They're also often milled for smoothness, perfumed nicely, maybe colored or medicated.
Is the cold process used for these?
It's mentioned, yes. That method reacting at lower temperatures without boiling, can be good for preserving the qualities of delicate oils used in some fancy toilet soaps. But settled boiled soaps and remelted soaps are also used as bases for toilet soaps.
And milled soaps, they feel different, smoother.
That smoothness comes from the milling. You take dried soap flakes or chips, run them through rollers mills again and again, mixing in perfume and color. It makes the soap really dense, fine-grained, homogeneous, lathers well, holds scent longer.
Okay, then textile soaps. They must need to be different.
Totally different needs. For washing fabrics, especially delicate ones like wool or silk, the soap needs to be neutral. No excess alkali, no harsh stuff, usually no rosin either, because that could damage the fibers. The book even mentions patent textile soaps, specialized industrial formulas.
And the miscellaneous category.
A catch-all for niche stuff? Shaving soaps needing a really rich, stable lather. Floating soaps, they whip air into them during crutching.
Ah, that's how they float.
Yeah. Ether soaps with solvents for extra grease cutting. And other specific soaps for the wool and silk industries. Lots of variety.
Chapter 8. Soap perfumes. The smell is so important. Hugely important for consumers. This chapter talks about where the scents come from, mainly essential oils.
What are essential oils, technically?
They're volatile aromatic liquids extracted from plants, flowers, leaves, wood, roots.
And the book lists loads of them.
Oh, yeah. Anise, bergamot, citronella, geranium, lavender, lemon, neroli, peppermint, rose, ylang ylang. Lots of familiar ones. It even gives technical data for some specific gravity optical rotation things perfumers use to check quality.
What about artificial scents? Were they using those too?
Yes, artificial and synthetic perfumes were definitely coming into play. Things designed to mimic natural smells or create completely new ones. Examples like amyl salicylate, heliotropin, synthetic musks are mentioned.
Gives them more options, I guess. More options, often more consistency, sometimes cheaper than the natural oils. The book stresses that the choice of perfume really depends on the soap's type and quality. You wouldn't put expensive rose oil in a basic laundry soap.
Makes sense. Chapter 9. Back to a byproduct. Glycerin manufacture and purification. We said it's leftover from saponification. Valuable stuff.
Very valuable. Glycerin, or glycerol, has lots of uses. This chapter explains how they get it back from the spent lye, mostly by evaporating off the water and salt to concentrate the crude glycerin.
Crude glycerin, so it needs cleaning up.
Definitely. It needs purification.
Yeah.
Distillation is key. The book mentions different grades like distilled glycerin and even dynamite glycerin.
Dynamite? Seriously?
Yeah, highly purified glycerin was a key ingredient in making nitroglycerin for dynamite. Also, decolorizing with charcoal to get it really pure and clear. The chapter also notes that how much glycerin you get depends on the type of fat you started with.
Fascinating connection. Okay, Chapter X. Analysis of raw materials, soap, and glycerin. Quality control time.
Exactly. Just as important then as now. You need to test your ingredients, your final product, and your byproducts to ensure everything's consistent and up to standard. The chapter points out that while they gave average figures earlier, real batches vary, so you have to test.
What would they test in the fats and oils?
Key things.
Yeah.
Free fatty acids affects how much alkali you need. The saponification equivalent or value tells you exactly how much alkali is needed for that specific fat, and the iodine value measuring unsaturation, like we discussed, checks if the raw material is right for the job.
And the finished soap, what tests there?
For the soap, total alkali, any free alkali left over, you want very little. The actual fatty acid content, the cleaning power. Water content affects hardness, and any fillers added, basically checking it meets the spec and is safe.
And for the glycerin?
Purity is key. The percentage of actual glycerol, also ash content, checking for inorganic impurities, and any leftover fatty acids. Standard quality checks.
Right. Final chapter, Emily. Statistics of the soap industry gives us the bigger picture.
Yeah, it's always interesting to see the economics. It has UK data going way back to 1801, showing production, consumption, exports up to 1851. You can see how the industry grew and how things like taxes affected it.
And more recent data for the time, early 1900s.
Yes. Import-export stats for household and toilet soaps around 1900 and 1907. Broken down by country, showing the global trade network for soap even then.
Did it give a sense of the UK industry's size?
It did. Estimates for the number of soap manufacturers in the UK and the capital invested shows it was a pretty significant industry.
But not just the UK.
No, it includes some production figures for France, Germany, the US, even Japan. Gives a little context on soap making as a global industry in the early 20th century.
Well, that was quite the journey through the Handbook of Soap Manufacture. I mean, I'm genuinely amazed at the sheer depth of science and, well, fiddly detail involved in making something we just use every day. without thinking.
It really is something, isn't it? From the molecules doing their job, the different fats, the boiling, the fitting, the finishing, all the way to the global statistics. It's far more complex and, frankly, more interesting than you'd probably guess.
Absolutely. It gives you a new appreciation for that simple bar of soap. All those moments, the triglyceride saponification, the nigre, quite remarkable.
It is, and it makes you wonder, doesn't it? If soap is this intricate, what about other everyday things we take for granted? What hidden complexities lie behind them?
That's a great thought to end on. Maybe something for another deep dive.